welcome everyone to the third of our seminar talks. And I'd like to talk today a little bit about how to think about machine learning. So different approaches that people employ to understand how things work. I believe there's still more questions than answers, but I think that's what makes it so interesting to mathematicians in particular. And as is tradition for us, I want to start with the seminar principles. So again, questions, remarks are welcome. Please interrupt. And this is a learning seminar, so we are not experts at all, under no measure. And we like and love examples. So if you have any, please let us know. Okay, so just sort of a view on, or sort of a very general view on what is supervised machine learning. So we're given some data, xi, yi, and we assume that the yi are given by a function of some xi. And then we make up a model. This could be a linear model or any kind of model to approximate this function capital G of the truth. And there are some parameters that we want to determine. So that's our goal. Find those W's here such that our model G is a good approximation to the truth, capital G here. And how do we do that? We have a training phase. And in the training phase, we just take the argmin of some loss function that tells us somehow the sort of closeness of our model and the truth. And this uses all the data here that we're given. So a finite set of data. But that's not really what we want. We want to know the truth of this G. So what we really want is an expectation value of this, or the expected value of this loss function, where the x are now drawn from the probability or the probability measure from which the data originate. Okay, so that's the actual thing that we're interested in, and that's called the generalization. So if we look at that, we can identify three. So we have three separate aspects of this machine learning enterprise here. First one is the approximation. So that considers the model that we're choosing here. So that defines a so-called hypothesis space. And if our function lies in that space, well, that's very good, but typically it won't. Okay. So we have to make a choice here of this hypothesis space. It's given implicitly through our model choice. The second one is in this training phase, the optimization. How do we find this W hat here in the training phase? So what algorithms do we use? How is that energy landscape looking? Can we expect to find a minimum? Can we expect to find a global minimum? And excuse me. Then finally, it's this issue here of generalization. So how good is the model that we find after optimization, where we establish this W hat? How good is that on unseen data? Okay, so I want to kind of separate those three issues here, and that's nicely done in a cartoon. So I stole this from Xiangqiao Li here. So H is the hypothesis space. So that's where our functions live that we model. That means our model, the truth lives somewhere outside here. So the best we can do is this G bar, and we start with some model G and our class with some kind of initial guess for our weights. And then we let the optimization algorithm do its work to find our W hat. And then the generalization issue is, okay, actually what we want to know is how good is that in terms of approximating our capital G, the truth, or we can ask, at least within that function class, how close are we to that G bar, which would be the optimal under the constraint that we chose the wrong hypothesis space. So I'd like to sort of talk a little bit about some of those aspects, the approximation and optimization and generalization, and what people, kind of methods or perspectives that people use to understand them a bit better. So for optimization, there is a conundrum that gradient descent, which is probably the simplest method that you can think of doing optimization, works very well. And it seems to work even better the larger the network is. So in order to understand that, people have used lots of different perspectives, but one that I want to discuss here, it comes from statistical mechanics and involves spin glasses. Then we already discussed this in, I think, in the tutorial or the programming, the hackathon, is that there's this momentum that tends to help us finding a method. And I want to try and understand why, if you have this so-called momentum, I will explain what that is in more detail, why that is actually helping in optimization. Then I want to talk about this approximation error and kind of want to talk what type of function spaces can we construct and what do we want from this function space. And I'm going to talk about reproducing kernel Hilbert spaces there a little bit, and then talk a little bit there also about the generalization order. And if time permits, which I doubt, I will also talk about deep residual networks and how, again, what I'm going to call the continuous, or not me, but what's called the continuous time perspective will help. Okay, so let's start, and let's start with the optimization aspect. And let's look at the landscape of loss functions. So here we have a typical loss function, mean squared an error here. So yi is supposed to be approximated by our function g hat, and we want to find the w's. So this is a non-convex function typically for the weights w. And so there's going to be lots of minima, maxima, saddle points, and all that. So simple gradient descent should not work. You should get stuck somewhere here and would not find the minimum, right? The optimal minimum. So that's bad. But an observation is that gradient descent actually works very well, or its sort of stochastic modification works very well, and in particular works really well in high-dimensional deep networks. Okay, and it doesn't work so well in shallow networks. So can we understand that? And there is sort of an observation. I mean, this is all these observations are kind of anecdotal, right? They're kind of, there's no theory behind that. They're kind of observations that people who tried those methods found. And one is that shallow networks have, in some sense, the same expressivity as a large network. So you can, you can approximate a function if you know kind of what it is very well. So it has to, the guess is that this has something to do with the actual optimization or with the energy landscape rather than with the expressivity. Okay, so let's explore that. The question was that the first point here, that this is empirical, and the question is if the second one is empirical too. Yes, that's empirical. Yeah, so these are all observations that people did, when they found that, and they tried it out, right? Kind of just, but on examples. So there's no general theory so far. So the basic intuition is the following: that we have just very few minima, and so gradient descent can find those minima. And a very simple argument is the following: imagine if you have a minimum, you take your Hessian, then all the eigenvalues are positive. Okay, so now imagine the sign is drawn by coin tossing. Okay, so you have a fair coin, and with probability 1/2, it's negative. With probability 1/2, it's positive. So in order to get a minimum, you have 1 on 2 to the n, if n is your dimension, probability of getting a minimum. So from that kind of probabilistic sort of view, you kind of think, okay, minima are rare, so that's good. But we kind of need a bit more. We want sort of, if we have a few minima, we want them to be sort of close, right? I mean, not close necessarily in W range, but close in terms of that the value of the loss function at the minima are close. Because when I hit maybe not the global minimum, I still hit something that has a loss function kind of close to the global minimum. Okay, so that's kind of what we want. How people thought about this, or one way to think about this is sort of reading through spin glasses. So that's kind of topical because of the Nobel Prize to Parisi, who got it for his work on spin glasses. But it started sort of I want to go, before I talk about spin glasses, I want to talk first about what spin systems are. And so it started with Ising in the 1925. And what they tried to understand was in physics phase transitions. So if you have something called a ferromagnet, then if it's very, very hot, there is no magnetization. And if you cool it down, you suddenly magnetization of that material starts to emerge. So we have a phase transition. And people wanted to understand how do they come about. And so the simple model that they have is they say each atom, think about it like a magnet. So an elementary magnet that has your north pole up, north pole down. So that's a spin up, spin down. And now these spins or these atoms, they live on a lattice. So it could be like a one-dimensional lattice, or it can be two-dimensional lattice, three-dimensional lattice. Okay, and they start to interact. And if they are ferromagnets, then spins, neighboring spins, want to align. If they are anti-ferromagnets, they want to take the opposite direction. Okay. This function h here describes this interaction, or it's an energy of the system that describes the interaction between neighboring spins. So I and j's are neighbors. Okay, so if all the j's are positive, we want to find the minimum of this, right? Or that will be the minimum. If they ignore boundary conditions, have them kind of on a ring, then they will all, line up in the same direction. So there's a minus here, so we're gonna get a minimum of this symmetry. That's the minimum we want. Okay. Actually, Ising, this is just a historical note. Ising was actually very disappointed because he couldn't find a phase transition in 1D. So he thought, okay, that model doesn't work. But then later on, Saga and so forth showed that you can get phase transitions in higher dimensions. In one dimension, there's not enough interaction to combat entropy increase. So you can't do that. Okay, so what are spin glasses? So in a spin glass, these J's, these coupling constants that tell us, are we attracting or do we want to repel? They are not sign definite. Okay, so what then can happen is, for example, the following. So let's say we have here our 4 atoms, and let's say these 2 atoms here, they have a plus J, these 2 have a plus J. This also has a positive sign, but there's a negative sign here. So let's just start with a spin up here. Then if I want to minimize with a plus, that one should be up here too. There's a plus here, so that one should be up too. But now I have a problem. If I want to satisfy this here, this interaction, then I should get my spin up. However, this one tells me that if I look at this spin here, I should be down. So the system is what's called frustrated. It's, there are these different configurations that have the same energy, same minimal energy. And how do you choose them? So it would be initial conditions, whatever, right? So here you would have 8 states, 2 for each. Oops, 2 for each of those. And so you have 8 states, and they would have an energy of, what is it? You get 1, 2, 3 for the J, and then of -2. Okay. So it's degenerate. You got 8 states of -2. So this frustration leads to something that we call metastability. So where we have several minima and they can get trapped everywhere. So that's a problem for us. Okay. One remark here for Ising. The Ising model actually, I'm not going to talk about the Ising model. I'm going to talk about a different model. It's called a spherical spin glass model. But Ising models have been directly, so those ones here, have been directly used to understand networks for so-called Hopfield networks. So Hopfield networks, this was something from the 1980s, where people looked at associative memory systems, so systems that can have, like, I heard once that a frog can sort of distinguish 4 patterns. So there's something like, suddenly the vision becomes dark. So that's like a heron or something, Then the next one would be like something moves and enters the field of vision and stops, or something keeps moving. And then the other one is something small and round in erratic motion, moves in the field of vision, and they all trigger different responses. So the first 3 trigger escape, and the other one, releases the tongue and thinks it's a fly. And apparently, whatever happens in the vision, in the vision field of the frog falls into one of those patterns. I mean, that's probably also a pattern where don't do anything, just keep enjoying your life. But that is, so people try to build these so-called associative memories or Hopfield networks, which is like a perceptron, the way we discussed it before. But now the weights are chosen such that you build this kind of energy landscape, so to speak, that looks like an Ising model, and then you just fall into those minima. Okay, so that's a direct. That's where Ising models really had a very direct link with networks. I'm going to talk about something less of a direct connection, but an interesting one that tells us about this energy landscape of deep networks. So because we're interested in deep networks, so these Hopfield networks are not the focus here. And so I'm going to talk about what's called the Pspin spherical model. So that is a model where we have n spins. Maybe a little bit about the history. Like this is sort of looks a bit crazy here. People try to understand these phase transitions. There are also certain phase transitions for spin glass models, and they sort of amped up the complexity and found, okay, there's you don't see what you see in nature. So you have something like Curry-Weiss model, then you have like a Kirkpatrick model, and they didn't quite do what they wanted. So then I thought, okay, let's have a model where these spins here, so S are the spins there, there's n of them, but it's not just nearest neighbor, but you interact with p minus one other ones that are chosen from everywhere, okay? So even from far away. So this idea from far away came from Curry-Weiss models that you have these so-called mean field models where you, but that's not really relevant here. But then really what you want to have it on the cube, right? So you want to have it on an n-dimensional hypercube. You got your 2n corners there, and you want to do that optimization problem, but that's too hard. So you do kind of similar what people do like in n-cut or r-cut models, you do this relaxation model where you just allow now the spin to be a real valued variable, okay, to be real valued, not just to sit on those edges of on the corners of the hypercube, but you keep the constraint that the norm is equal to 1. Okay, so that's this constraint here. And so now the S, which is S1, S2 up to Sn, lives on the sphere. And that's a so-called Pspin spherical model. And then when people analyze this, they say, okay, these kind of interaction constants here, they're randomly chosen, okay, from a Gaussian. Okay, so that's a model, has nothing to do with neural networks so far. And yes, product, Si1 times Si2 times Si3 times Sip. So there's always there's P spins, all subsets of P spins are interacting. It's not, no, the question is, are these vectors here? These are not vectors, these are the components. Si1 is one component of the vector S, okay? So S is a vector that has S1, S2, S3, up to Sn. So these are my n things that can be up and down, my n atoms that can be up and down. And now I look at the interactions of P of those. Okay, so here I'm not going just over nearest neighbors. Are we still on a lattice? Or what is this like? Yeah, well, here you're actually on a complete graph, right, in some sense. Okay. If all the ji's are non-zero, yeah. And your interactions are given by a normal distribution. And the interactions are given by a normal distribution, that's right. Yeah. No, P is not equal to n. No, P has to be larger than equal to 3. That's the only thing. Okay. Okay, so that came up from physics, and all this, what I just told you about, why people were interested in this Ising model, is completely irrelevant for what we're going to discuss. There's no phase transitions or anything, but there is a connection between this Hamiltonian here of a Pspin spherical model and the deep network that I'm going to establish now. It's going to be painful. Okay, but first the result. So there was a series of papers by Offinger, Ben Arous, Czerny, and then Offinger and Ben Arous. And they studied the energy landscape of this this Pspin, spherical Pspin model. And they found the following. They found that all the minima, so if this is the Hamiltonian here. Oh, yes. As p equal to bigger than 3. I knew that and I forgot. I'll answer it. Yes, I have to answer. I have to look back why p has to be larger or equal to 3. I guess you don't. Otherwise, you had nearest. No, I don't know. I have to check. Otherwise, I think you have something like Curie-Weiss or something, and then there you wouldn't have that phase transition that you wanted to look. But I check it. I posted on the discussion board. Thank you. So there was an answer. There was a comment from the audience saying that p equal to 2 is trivial, but I can't see at the moment why it is trivial. I think it's because it's close to this Curie-Weiss model, where you don't have which you can solve trivially, but it's still random. Curie-Weiss has all the j's are constant. So I'll answer this later. Okay, so what did they find? They found, if you look at the energy, and remember h you want to minimize, that the minima are very close to the minimal energy that you can get. And then you have this sort of layered structure where you fill it up with saddle points with an index k. So the index is the number of negative eigenvalues. Okay, so think about the more negative eigenvalues I have, the easier it will be for gradient descent to kind of move down. And that index is increasing into here up to some minus h naught. And then up to here, you have saddle points where the index increases exponentially with the dimension. So that is fantastic result, right? That tells us that we got a couple of minima here. They are all close to the minimum, the global minimum, minus h infinity. And the higher I go in the energy, then the higher the index is, so I can travel down. Okay, so that's a beautiful result for spin glasses. So if I want to find the minimal energy for a spin glass, I can do it, right? But the question is now, like this is sort of homogeneous polynomial here of degree, random polynomial of degree p. So what has this to do with deep networks? And there was work by Choromanska and others from 2015 that explained that. So now the pain is going to start explaining this. So this is a fully connected network with p layers. Okay, so we have an input here, d-dimensional, and we have an output, one-dimensional, and in R, but we're going to do binary classification. So we have an output, but we want to have it something that only has, two labels. Okay, that's our truth. And we got weights in each of those layers. W1 is, like a vector here, and then I've got more here, and so forth. So I write this as we accustomed to, kind of, you have a linear transformation, move it up to first layer, put up something like a ReLU function, then another linear transformation for the next layer, hit it with a ReLU function, and so forth. Okay, until you come to the end. And then you end up with this thing that we know so far, that we've encountered now many times. Now I'm going to change the view on this. I'm going to rewrite this. This is the way we know how to do it, by not summing up over all the different paths that are possible. So the first sum here sums up over all the xi's, over all the d, or let's call it n naught, components xi. And then I start counting all those paths, all of them. Okay, how many there are? n1 times n2 times n3 times blah, blah, blah times np, a lot. Okay, and then each of those paths, if on this path here, at some stage, the ReLU function is such that it will be 0, it will zero it out, that path doesn't exist anymore, or doesn't contribute anymore, and I count that by aij equal to 0. Okay, so remember, I just comes from wherever I start here. Okay, and j refers to the path that I'm taking through that network. Okay. On the other hand, if all the ReLU functions are active, then it's just a linear evaluation. So I can just multiply all the W's, right? So Wij, k, so k refers to in which layer we are here, okay? And the J is again, you know, what type of, so 1, 1, 1, 1, that would be, you know, up here, okay? And so then this Aij is just either 0 or 1, okay? If you're active, you're 1. If you got zeroed out by any of the values along one path, you're 0. Okay, so we just rewritten it. It's on I, yes. So I.
It also depends on like the actual value.
That's right. Yes, that's correct. So the question was if Aij depends on X, and it wasn't a question, it was a comment, and it's a correct comment. Yes. It's different to Dirac, that was not a question. Read it. Okay, so now we start making approximations. First approximation is, we're going to say that the xi's are normally distributed from 0, 1. Okay. Then we're going to say that each of those paths has the same probability p. So these Aij's are some Bernoulli distributed random variable with mean p. Okay. So we can average over the a's, and if you see here, we just get, you know, replace this by the p, by the mean value, which is p or pi. Yeah. Okay. And now comes another approximation, which is then allows us to do another reformulation of the sum. So remember previously here, we sum over all the paths. Okay. Now, let's imagine in our network, there's some kind of uniformity there. So at each layer, we have basically, let's say, capital lambda weights. Okay, so it's uniformly distributed. In each layer, we have capital lambda weights. And they are now uniformly distributed. So in total, lambda to the power of p, so lambda times lambda through all the things is the number of paths that I can get. So that's gamma. So that's how we can define this lambda. And now let's, ik now tells us the weight or the connection of the k-1 to the kth layer. Okay, so we can now relabel all these ij's here through those ordering of the unique weights. And I'm going to just assume for now that each weight occurs only once. And then you can rewrite this as a sum over all those weight configurations that go up to lambda here. And the xi becomes this xi1, i2, up to ip, whatever weight configuration I'm looking at. And that now looks like the Pspin glass model. Okay, if we have an additional constraint here, that the sum here is also normalized, you know, that I live on a sphere. Okay, and that you can just say, well, in a network, you would do that by regularization, by just saying that your squares, the norm of your squares is not allowed to be, you know, is bounded as equal to lambda. Okay. Okay, so that now tells us that we can write under lots of assumptions that may or may not be realistic, convert a deep p-layer, deep network, neural network into a Pspin spherical spin glass model. And now we need to relate it to the loss function. Oh, you see, there were lots of assumptions. There was the assumption that the xi's are normally distributed. There was the assumption that each path was equally probable. And there was the assumption of this uniformity assumption. And there's some other trickier bits in that make these sums what I've kind of, you know, what is sort of glance over here. There's some other assumptions as well, you know, about the uniqueness of the weights and things like that. But it's yeah. Did that answer? I can't see the chat. Yeah. Okay. So, but we need the loss function. Here we only have the y, right? So the output, and this is the output. This is, remember this thing here was the expectation of y. I sort of abused the notation over all the a's. Okay. So now consider the following loss function. Remember, we're doing binary classification where we just take the absolute distance between the true label and the output. Okay, so the s here, so the true label can be s or minus s. I just flip the signs. And s, if I do binary classification, then that s, then I have to tune or normalize my y such that the maximum hits, like if I get the maximum of output of my network, then that's either plus, yeah, that's plus s, okay, or minus s. Right? So that I can interpret it in this kind of probabilistic way. And so I know what s is. And if these xi, 1, I2, IP, if they're independent Gaussians, then sort of you can say in law, this is not equal to s plus y. So now my loss function, I can relate to the actual output here, okay? And that means now we've established, let me go back here. We've established, so this is Joromanska et al., I think 2015 or something, and Ben Arus was also co-author here, that I can relate the spin here to the weights, and I can relate the Hamiltonian to our loss function, and I have this, you know, nice picture that I wanted. Okay, so that's where kind of statistical mechanics helps you to get an intuition, I would say, of why things such simple optimization algorithms such as stochastic gradient or simple gradient descent do work. Okay. So there's a minimum. So the question was, what does the label k correspond to in the neural network? So it was the Hessian around, you know, around of your Hamiltonian evaluated at a critical point, and now it's the Hessian, you know, of the loss function at a critical point. So the question was, what about the global minimum? We don't know if you're going to hit the global minimum, but what we know, what this theorem tells us, is that all the minimums, so only k equal to 0 are minima. K equal to 1 already is a saddle, right? Because there's one eigendirection with negative eigenvalue. Yeah. So all the minima are close in. This would then be L here, right? So they have roughly the same loss function, roughly the same value of the loss function. So you don't, even if you don't hit the global minimum, you hit something that's close. Okay. So the question is, what? How do we interpret this in a neural net? And it is, yes, we don't know that we're going to hit the global minimum. We might get very different weight configurations if we run, you know, from different initial conditions, but they all lead to roughly the same loss. Oh, that's a good question. So the question is in the chat is how much of this is linked to of the argument relies on having value functions as our activation functions heavily because, you know, we say 0 or, you know, we have this kind of product of the weights, which is just when we hit the linear bit. Yes, thank you. But I don't think we used very deep networks so far, right? We had 5 layers, and how many nodes did we use in the tutorial? I mean, it's not, but on the other hand, the learning tasks might also be simpler. But yes, it is definitely consistent with what with this, yes. So it should go better, even it should become better. So Martin wondered that, you know, what I presented here seems to rely heavily on choosing ReLU functions and on choosing this particular loss function. There's another loss function called the hinge loss, for which you can also show it. I didn't show that this year. And yes, that is correct. However, I see this more as an intuition, kind of, because we see this in real, in real systems, we see that behavior, that also, what Jody just said, that we see that even in our tutorial. This is just kind of developing some intuition of what must happen. And in this case, you can show it. I mean, this is one way of looking at it. There are other ones that kind of, say, well, all these minima are kind of collected through valleys. So you can just, go from one to the other one. I mean, there are lots of kind of observations and ways to try to understand this. This is just one. So here is a question. You're explaining that the training loss of all minima are close to 0. Is there any study of the generalization error at the different minima? Good question. First of all, I don't say that it's 0. I'm just saying they're close to the global minimum. And this does not address generalization. I actually couldn't find an argument about deep here, right? Because this is just the number, kind of the total number of neurons, I suppose, right? The total number of weights. So it could also be widths. So I'm not 100% sure, but I don't think it addresses really the depth, just the general dimension. Change of topic, change of gear. A different aspect of optimization. So this is just a screenshot from one of Joel's lovely notebooks. And this is the optimization routine, SGD, stochastic gradient descent. And there's something called momentum. And if people played with this momentum, they may have realized that, the result will be slightly different. And I want to talk about this momentum. And also, people will have noticed this LR here. And that is the learning rate that we can also choose, right? In each step, how far do we, advance forward? So, zoom. No, oh God, not zoom. No, that happened to me before, and I don't know how to get out of this. Ah, yeah. Okay. Up here. Okay, so this is stochastic or gradient descent method. You have some Wn. You go minus, in the direction with a rate eta of the gradient of your loss function, and you get an update Wn plus 1. And typically the loss function is like an empirical risk where you just average over all the individual loss functions at your of your data. And you evaluate this at time n and at time n, and you get your n plus 1. So this works, and we just discussed, one way of trying to understand why it works so well. I mean, this is seriously the simplest method that you can think of. But the situation where it's quite slow. For example, imagine your loss function looks like this. So where we have one direction, so cross section here, where we have a very steep, minimum, and then if we do a cross section here, we have sort of a very shallow kind of minimum. And if you do that, and if you start here, you're going to go along the steep direction, and you kind of can oscillate here for quite some time before you reach the minimum, right? And one method that was proposed to mitigate against these oscillations are these so-called momentum methods. So I'm going to talk about a particular momentum method. It's Poljac's heavy ball method from 1964. There are other methods. So Nesterov in the 80s has this accelerated momentum method. These are kind of two main methods that people use. And I want to show you sort of a way of looking at those methods that might explain why they actually work better. So if I write down these Poljac's heavy ball method, so this here you recognize is our standard gradient descent. And then they just have add some memory in there, keep some information on what you just done before, Wn minus Wn minus 1. And that sort of memory is parameterized by gamma, which lies between 0 and 1. Okay, and then was shown that if you do that, you suppress those oscillations, right? So you converge quicker. So let's try to understand this. You can write this here by subtracting two of those equations and write it in this way here. Again, eta is the learning rate. And if I now interpret here eta, the learning rate, as some kind of time stepping, then this is a consistent approximation of the second, or it's a second order approximation of the second time derivative. And this one here is if evaluated at n, and this one here is a consistent discretization of a first order time derivative if I interpret again eta as my time, right? So there's a continuum. So there's a continuum limit to this. We can say this is a consistent finite difference discretization of this ODE. Okay? So we have an ODE here that sort of describes a small mass. So eta kind of survives this learning rate here. It's like it's now your mass, the mass of a particle that moves in a potential well, but then is damped, and we have a damping term in here. Okay. And if I write this as a first order system of equations, I end up here. And now, since eta is small here, we have a slow fast system. So if I just write v dot equal to 1 on epsilon blah blah blah, so what's slow fast? Eta is small, so the right hand side, like the v, will do this. That's what I kind of call fast here, whereas the w is kind of, it has an order 1 on an order 1 time scale. Yeah. So you can show that for this slow fast system that there's an attracting invariant manifold. So where the y after an initial transient is slaved to, the v is slaved to the w. Okay, and the kind of this exists sort of in an approximate way. And the zeros order approximation to this manifold is just set eta to, no, I really set it to 0. Set eta to 0. And then you have this algebraic relationship now between v and w. That is sort of a slaving relationship where whatever w does, v follows. Okay, so that's where the dynamics happens on this invariant manifold. And you have now slow dynamics on this manifold that is sort of approximated by that relationship here. So now I want to know what's the slow dynamics on this manifold. Well, I just insert the fast, now my manifold solution of v into the equation for w. So I insert this here into here, and I end up with this equation. So that looks, if you just ignore this here, that's our standard gradient, right? And like that, if eta again is a time step, that would be, we do an order discretization, then we are in standard gradient descent. But look at what's happening here. Gamma is between 0 and 1. So this is large, or larger than 1. So we have, in effect, a larger learning rate. Okay. So these momentum methods, so this is, they're just one way of getting an effective larger momentum, a larger learning rate. So you learn quicker, okay? They converge quicker. So the kind of, I said I want to talk about ways to look at machine learning algorithm or machine learning. So the methodology here is trying to understand these discrete methods that we have in general. Also we have like a discrete neural network. Here we have a discrete algorithm for our optimization algorithm by going to the continuum limit, and then because continuum limits are much easier to understand, and so this is a sort of continuum perspective on these discrete algorithms that we can learn about something. Why is learning? It's not better. It's faster. It's faster. It's only faster. So it's the same. Based on the time scale. Okay, so think of this as a time scale, the 1 on 1 minus gamma, which is 1 on 1 minus gamma is larger than 1. That's right. So there was the comment from the audience about the oscillations, that they're a discretization problem, because the learning rate, it could be too large that you get into the opposite, on the opposite part of the valley. Like if you had a tiny, tiny step, yes, you can do it. However, it would take forever. So you think of, so the question is, does it help to know higher derivatives of the loss function? Yeah, you can think about that, right? If you have sort of Newton methods or something, right? You can kind of adjust your learning rate by the eigenvalues of the Hessian, right? So yes, I don't know how practical that is and how good it is to actually estimate them and how expensive or cheap. Yeah, I would think it would be very expensive to do that too. So I think that's why people kind of don't want to use something like Newton or where you kind of adjust the learning rate depending on the curvature. Because it would be good, right? If you have like a plateau or something, right? You want to take a very large step, right? So question was, can you use higher derivatives to help your learning? So idea is if you're flat, then you want a large step, whereas when you're really steep, you want a small step. So can you use that sort of local curvature? But then the comment was, if you do that, then it's very expensive to evaluate the curvature. So that's why these methods are preferred from a practical point of view. But then coming back to the first part of the seminar, it's also okay because you have those, the minima are kind of clumped together in value, not necessarily in W space. But also the question is, can you build a continuum model of a neural network to see where the minima are? I don't know. I mean, there's something like, I doubt I will get to there. There's one particular network architecture where you can do a continuum limit and you can learn something about it, how to do optimization. It's basically solving the adjoint model. So that, yeah, these ideas can help there. Thank you. Okay, before I continue, so Harini already said during the lecture that it's the reason why p equal to 2 is not interesting or is trivial. She just explained it to me, is if p is equal to 2 and you only have two spins, then if you take the derivative, with respect to those spins, then you just basically have a linear system of equations that you can solve, so everything is fine. So thank you, Harini. Yeah. So indeed, it was trivial. Okay, so some comments on generalization. So question, once we trained a network, how well does that learned network perform on unseen data? And sort of in classical statistical learning theory, what you see is the following curve here. So this is the empirical risk sort of for the testing data, and then for unseen data, the training data, and then for unseen data up here. So what you see is that the higher the capacity, so think about capacity as just the number of parameters for the moment that we're going to use, so how, the dimension of your network and so forth. So the more parameters I have, the better I can fit the data, and so I can drive down the training error, right? But at some stage, I might overfit. So I might, just fit exactly the data points, and that will not generalize very well to new data. And then you see this kind of testing, the test error going up again, because, you chose your model quite badly. So this is a classical thing where we would just say this is, past this sort of sweet spot here. This is sort of an underfitting where we should increase the capacity, the dimension of the network in order to still drive down the test error, and then followed by the regime, this classical regime of overfitting. Okay, so that's classical. That's kind of what you see in statistics books and so forth. Now the cool thing comes. What happens in deep networks, well, that's what it kind of was said, is you have this double descent curve. So once you reach sort of almost zero area, so when you completely, like if you really fit perfectly the test data, no, I get it wrong, the training data, you drive down your test data, okay? So my understanding is that this is still an open question. There's some very interesting works being done on trying to understand that. Mikhail Belkin and people like this work on that. I found that fascinating. And what's happening here? Want to say that this has to do somehow with the expressivity, right? We increase the dimension. And to some sense, why wouldn't you try to bring your error down to zero, your training error, right? Otherwise, you haven't really made use of your network. But it's expressivity, but on the other hand, we just also learned it has something maybe to do with the optimization. And I think it's still not quite clear, to me at least, what are main drivers for this double descent curve. But now the very interesting observation here that has been made by Belkin and then also by Hasties, that this already appears in kernel methods, and it already actually appears when you just do normal linear regression, okay, without regularization, as I understand. So that's a recent paper. I haven't read it yet, but this is not just a property. This double descent is not just a property of deep networks. It also occurs in kernel methods and in yeah, but that regularization is kind of decreasing the capacity then, right? Kind of you don't. Yes, regularization is one way of using sort of prior information. No, this is a thing that I don't understand. It's actually when the regularization goes to zero. I do not understand that. I have to. That's something I would like to understand. I think these kernel methods, they work really. They have this double descent. That's my understanding. I haven't looked deeply into this. My understanding is that when the regression, parameter goes to zero, that's when they show this double descent or tiny regression. Yeah, but I don't know much about this, unfortunately. Okay, so about the expressivity now. Okay, so the thing is, if you want to fit data or something, then there are lots of functions that are consistent with a given data set. Okay, I can make up gazillions of those, and they will fit, and there will be good models on those testing data. So what one would like to use is some kind of prior information. Okay, so Joel mentioned regularization. That is some kind of prior information. If you do L1 regularization, we have our prior information is okay. We have sort of a sparse in parameter space. We want to be sparse. And sort of a side comment that we may or may not get to at some stage is that regularization, you can also, if you adopt a probabilistic point of view, you can interpret regularization in terms of priors, if you adopt the Bayesian point of view. Here I want to talk a little bit about function spaces. So the choice of function space, how does that incorporate also certain prior information. So, and I hope I want to get rid of this. So I want to go back, since this problem of generalization already appears in kernel methods, and since we talked about kernel methods, I want to talk about a particular function space that's called the reproducing kernel Hilbert space. I'm going to give you an example in a minute. I first want to introduce what it is. So it's a Hilbert space that has an inner product, and we call it a reproducing kernel Hilbert space if one member of this Hilbert space, which we call a kernel, is such that that kernel is a member, is part of the Hilbert space, and that this kernel has what's called the reproducing property. So if I take the inner product of a function f, so f has to live in that reproducing kernel of Hilbert space, and the kernel now evaluated at x, then this is an evaluation operation on that function f at x. Okay, so you hit a function like an element from that Hilbert space with the kernel evaluated at x, and that spits out the value at that function. So this f here is an object, and that is now evaluated at x. Okay, so I want to give you an example to show that you actually have already used those reproducing kernel Hilbert spaces without knowing it. It's like the prose, you've been speaking prose. So let's take the example of the XOR function that we've already came across. And we know that if we introduce these features phi here, where we sort of blow it up into R3 by some kind of nonlinearity here, then we would be able to linearly separate those points. Okay. So now, we can define, let's define a sort of a kernel Hilbert space here. So we can build a kernel out of those features by a scalar product here, a scalar product in R3. So this is just the sum of all the components of these phi1, phi2, and phi3, evaluated at x and at x dash. And that's then our kernel x dash. So phi transpose phi. Okay. Yeah. Okay. And the inner product that we have on this reproducing kernel Hilbert space, and even finite dimensional, that's just a standard inner product in R3. Okay. So let's look at functions. So let's look at linear functions. We have linear functions. We can define them in this way. So f1 is a component of, of x1, f2 of x2, and then of x1, x2, the component we call f3. So an element now of this function space is this vector. And if we want to evaluate this function at a point x, well, we just take the inner product here of that vector with our feature, and we get the evaluation at a particular x. Okay, and the kernel evaluated at some x, that's just the phi of x. So the kernel is also an element of that reproducing kernel Hilbert space. Okay, so we have this, what we've done there already corresponds to working in a reproducing kernel Hilbert space. It's finite dimensional. It doesn't have to be finite dimensional. Okay. Some remarks. Powerful remark. There's no restriction on this x here, right? So where all the small x's come from, there is no restriction. Yeah, but here the function maps R2 into R, right? The functions of this reproducing kernel Hilbert map R2 into R. But the data, that was the point here. The data, there is no restrictions on them, right? So this could be graphs, this could be images, and you're just given some features, some functions of the data that you can produce. So that is, at the moment we just assume in this kernel methods that they're given. Someone who knows a lot about the system gave us now these features. I mean, in deep learning, we said we want to learn those features, right? But at the moment, we just take them for given. But it can be anything, right? It can be an image, a speech, something, sound document, written document, anything. And it doesn't have to be an element of the Hilbert space or anything, right? It doesn't have to be a Hilbert space. It can be anything, right? No, there's no restrictions on X because we work with these. Oh, F, yes, that's right. It's a restriction on the functions F. There's an equivalent formulation that some people might like better, which is just that the evaluation operator, so that takes an element from the Hilbert space, this function F, and evaluates it at a point X, that one is continuous. So kind of means that, something like this, right? That we have there's a function C, a constant C, that I can sort of bound the functional value at an X by the norm in Hilbert space. Okay, so you get convergence now, pointwise convergence, which is very nice. That's what you want, right? So if you converge in Hilbert space, you also get convergence of the functional values. So that also shows you that L2 is not a reproducing kernel Hilbert space, because there's no way you can control a functional value by the L2 norm. The integral doesn't care about a point, so at each x I can shoot it to infinity, and the integral doesn't see it. Okay, so From that perspective, it's not a reproducing kernel Hilbert space. And also, if we go back to that other definition that doesn't use kind of the continuity, but that formulates in terms of this existence of this kernel, the evaluation operator is a delta function, and the delta function is not in L2. Okay. So one way to think about these kernels is like a modified delta function. Okay. And this formulation here gives rise to kind of, this is sort of the theme that we had from the very first lecture, that we have some space X, we take, some kind of data, we blow it up to a high dimension, into this kind of high dimensional Hilbert space using the kernel. And then after that, we can do linear operations. Okay, so that's, again, kind of that sort of coded, hard coded into this, into this framework. There is the following sort of triangle here. So the first thing is that there is a unique relationship between a reproducing kernel Hilbert space and a positive semi-definite kernel. So for any reproducing kernel Hilbert space that you have, there exists a unique kernel. And vice versa, if you make up a positive semi-definite kernel, then associated with that is a unique reproducing kernel Hilbert space. Okay, so that's this more Arons-Jan theorem here. And then there is another correspondence here, but that's not unique, between a kernel and a feature map. So if I have features phi, then I can express that kernel through features. So here the phi's would be eigenfunctions of a kernel integral operator, but it's not unique. Okay. So one example maybe to show you non-uniqueness. Someone asked that before. So phi of x equal to x and phi of x equal to 1 on square root of 2. No, 1 on 2. Xx, for example, gives the same square root of x, right? Sorry, that gives the same kernel, okay, which is x squared. So not that. Okay, now phi transposed is gives me x, and here I also get an x for the kernel. Okay, so it's not unique. You can get the same feature map. You can get different feature maps. You can get the same kernel. Okay, because of the inner product that you have, right? It's the same reason why the inner product is like the norm of a vector is non-negative, right? Yeah, if you're an integral operator, you would want, you want something like sum of alpha 1, alpha I, alpha j, kernel of xi, xj. This is the equivalent here of, diagonalization. So you write it. I mean, these would be matrices, the phi star here, right? So you have your K would be a matrix, and then you diagonalize and you do your spectral decomposition.
So these lambda i's are non-negative? Are these lambda i's meant to be non-negative, or are they just real numbers?
That would be non-negative, yeah.
Okay.
For the matrix, it would just be that the quadratic form is, right? Positive, or all the eigenvalues are non-negative. Or the quadratic form, but that's okay, it's semi-positive. So let's say we have some features and we write our f as this linear combination of those features. So one example would be a linear model. We can define the inner product as just an fi times gi, so the components of those these coefficients here, and we can define the kernel. I mean, this is what we've done for the XOR function already. And then you can check this reproducing property, and you can check that K belongs also to the kernel Hilbert space, reproducing kernel Hilbert space. There's an alternative formulation for this, or expression of this function in terms of the kernels. Okay, so you can write, rather than writing it this way and having these, calculating these inner products here, you can express anything in terms of the kernel. And also the inner product here is expressed entirely in terms of the kernel. So there was, I think in the first talk, there was a comment about these kernel methods. So this is in some sense why people like it, because you don't have to, this formulation, you don't have to go into this high dimensional Hilbert space, look at all your features, which are very high dimensional, multiply them together, which is very costly. You just work directly with the kernel, okay? So it's an equivalent formulation, and it's one that is actually used from a practical point of view. Okay, so now I want to talk about a particular choice here. So I want to stay in this. I want to stay with the feature maps. I don't want to go to the kernel. I know that if I have a feature map, I know that there's an equivalent or corresponding kernel. But I want to keep with these feature maps and want to discuss a particular type of those kernel methods, and they're called random feature maps. Okay, so random feature maps is the following. I have an X, let's see an RD. I hit it with a linear transformation where the bias and this matrix here are drawn randomly, but they're fixed. We draw them randomly, but they're fixed, okay? And then I threshold component-wise. So this whole thing here lives in some Rm. And then I transform back into whatever dimension my y is, okay? So sigma is some thresholding function. So it can be the one that I'm going to use here, and the one that's kind of mostly used for this random feature map is a tanh. Okay, so it's something that's again evaluated component-wise. For these random feature maps, you have again a universal approximation theorem. So this is Pspin from the late 80s. But again, the universal approximation theorem doesn't tell you how to choose the parameters properly, in particular those ones here, right? Like for which parameters here it will work well. So when I played around with those, what I found is, it sort of makes sense. You give it input from X, so X comes from some kind of probability distribution, and you want that the argument of this tanh doesn't live just here where it's, you can't distinguish anything anymore because it's just saturated. And you also don't want it to live close to here because that's, would just be a linear model. There's no need to do anything else. So you want to kind of explore this sort of nonlinear parts here. Okay. So the question is, why do we expect them to be good? First of all, you could think, well, hold on, if I just, take these functions phi and I sum them up, I might actually have a curse of dimensionality here, right? So take the sigmas not as tanh functions, but take them as Fourier modes, right? So that means we have a discrete, like a Fourier transform here. Okay, and then we know if we want to approximate any kind of function f with our Fourier series here, then we have this curse of dimensionality. Like if we have, per dimension, if we keep m nodes, and for the other dimension another m and another m, so we got an exponential kind of increase in the number of modes that I need to achieve a certain error. So this error here is bounded by alpha, is sort of relates to the smoothness of the function, and the dimension comes in here. So for higher dimensions, increasing, the number of modes m, I get less for my, for that increase. So that's this curse of dimensionality. There's also this kind of smoothness here that so that we have quicker convergence the smoother the function is, right? Which is again something that universal approximation theorem doesn't tell you kind of how fast you converge. For that, you need something like Taylor, right? That's right. So it kind of tells you that there exists some kind of W and B such that you can approximate, any function arbitrary curves. Yeah, but it doesn't tell you how to choose them. Thank you. Yeah. So now think about this here as, or the Fourier representation, think about it as an expectation value. Okay, so we got the integral here over some measure, will be, typically the Bake measure here over, that you take your omegas from. And then what you do here is you sort of take a uniform grid, right? You take, you discretize your Fourier space, uniformly, and then you calculate that series here. But if I write this now as an expectation value over this, where I draw the omegas from this measure pi, so the Bake, say, but randomly, then I can use a Monte Carlo approximation for this. I can evaluate the integral, by drawing now random samples from pi. Let's call them omega twiddle. And now sum up here my, take only this kind of omega twiddle modes. And so they're randomly drawn. And then when I do this, well, we know from the law of large numbers, we converge to F. Okay, so the more modes we take, we will converge. It's the law of large numbers. And from the central limit theorem, we know that this object here, the fluctuation, the difference between the two, is just a Gaussian random field. Okay, so that scales with 1 on square root of the number of degrees of freedom that I have. Okay, so by doing this kind of random drawing of the Fourier modes, we get a much better convergence. We don't have this curse of dimensionality. However, careful, the constants, where did I always do that? The constants might be quite large. Okay, so it might still be impractical. So it's not the solution to everything. Okay, and there's a nice result. It's actually even better than just square root of m. So what Rudy and Rosasco showed is that you only need square root m log m terms to get actually the 1 on square root of m convergence. Okay, so you're doing pretty well with those. And I still have time. Okay, that's good. So I wanted to stop here for the for this reproducing kernel Hilbert space excursion, kind of to set a bit more formally the scene for these kernel methods, and then introduce a model or an architecture, which is very, very simple. It's just one layer, and where the weights, are drawn randomly. So there's no optimization to be done in terms of backpropagation or anything, fancy. The only way, like if you want to approximate, is to determine these weights here, W, right? And that's again linear. So we're in the linear framework here, and we can just do least square regression or anything to get those W's, right? So that's a very, very attractive framework from a computational point of view. And it has very good, kind of very fast convergence properties. But I quite like those because they're so simple. But of course, they're anything but deep. Right? Yeah, the question was if I use these random Fourier modes as a metaphor of what's going on. Yes, because in Fourier we know this estimate here, right? We know how fast we converge. And that's, this is just to motivate why it's actually a good idea to randomly draw your features. Now FFT is good for a different. FFT does that assumes those uniform discretization in Fourier space. Oh, yeah. Oh, the question is there any argument also from an optimization point of view why they are so much better? There is, here you have a linear problem, right? So if you want to, let's say a y, now you got your kind of W and this kind of funny random features. Let's call them, I don't know, this whole thing, let's call this capital phi, right? So this would be that's least square. So this is convex and, everything is, so there is no optimization is needed. Yeah, that's right. Optimization is needed, of course. But it's given analytically, right? I mean, you can actually solve it analytically. There's a closed expression for it, right? I mean, you need to regularize and so forth if you don't have enough data. So, yeah, so here you would choose the A's, right? I mean, yeah. So here you find these ones, right? You find the linear coefficients that work the best. And M is typically very large, right? So M is much, much larger than D. So it looks like a neural net, right? Like a one-layer neural network, but they're fixed. We do not optimize. And so that's, in some sense, what these reproducing kernel Hilbert spaces are. They're a good space of functions that allow you fast convergence, right? They allow this is 1 on square root of M convergence, which is, you know, sort of the best you can hope for. And so in that sense, and they allow you pointwise evaluation. So in that sense, they're kind of ideal. They're the right choice for this setting. For networks, it's a different story, right? You need other kind of spaces. But I don't. There's something called a barren space for a single layer network, and you want a space that allows again this kind of convergence with 1 on square root of M. Okay, so there was a question about the universal approximation theorem. Why we learned why it's that it shouldn't be polynomial as a function last time. And then people may not have heard the answer. The answer why a polynomial doesn't work is basically Weierstrass again, because you would fix, if you choose a polynomial for your sigma, you fix the degree of the polynomial. So you can't, like in Weierstrass, you need to get higher and higher degrees of polynomials. So that's why polynomials don't work. But the tanh is not a polynomial. For the network, we said we don't want the flat regions because then the gradient won't work, right? Then the gradient is just flat. So we can't optimize. So we have a vanishing gradient, so the optimization will work. Here's no optimization, but if there is no information in those functions, they're basically constants, right? So this would be a bad way to approximate it. And if you take it too narrow around the at 0, where the tanh is basically linear, then you may as well use a fully linear model. Yeah, but God, I mean, there is still, if you change them a little bit, you can get. I mean, there's a region where there's a higher likelihood of getting good approximation. But I don't think that region has, is awfully big, measure 1 or something. All right. Thank you all.